decision trees are very rarely used by themselves in realistic machine learning projects. And the reason for that is that no matter how much effort you put into them in terms of doing pre-pruning or post-pruning, the reality is that they remain relatively weak machine learning models. They do tend to overfit quite much, and the efforts that you are making to address that overfitting eventually turns them into quite weak models. However, they do remain popular in practice because of all these things that we've discussed in some of the previous videos, in terms of the feature ranking and in terms of the simplicity of training them and in the simplicity of the pre-processing of the data. But to keep those strengths while addressing the fact that they are relatively weak models, you need another idea, and that idea is that of ensemble models. And I want to discuss in this video about ensemble models in several different ways with decision trees. These are some of the really most popular models nowadays on around decision trees. And I want to start with random forests. The key idea in random forest comes from statistics, and that has to do with how you adjust the high variance of the output of an experiment. And I mean, it's been long known that if you perform the experiment independently multiple times and you are averaging the result, that's going to cut on the variance. And this is something that we have seen, for example, also when we discussed in other lectures about cross-validation, the same idea that you would do this sort of independent test several times and then you would average. So here is a numerical example. If you have some binary classifiers and they are correct 70% of the time, and you say, you know what, let me take 3 binary classifiers working independently of each other, and I'm going to ask them to make a prediction, independent prediction for the same data point, and then I'm going to take a majority voting. So just this idea, all of these binary classifiers, they are 70% correct of each time. Just the idea that you make them work in parallel and then you take majority voting, that's going to increase, and this is a simple calculation, is going to increase the correctness, the probability of getting a correct prediction to about 78%. This goes even higher. If you take 5 binary classifiers, they work independently of each other on the same data point, you take the majority voting, and that's going to be correct 83.7% of the time. And this goes dramatically up. If you do, for example, 101 binary classifiers and you take majority voting, that can really go up to 99.9% being correct each time. So that's an interesting result, and that really also goes hand in hand with the idea that decision trees are easy to handle in terms of data processing and in general in terms of training. So this idea that you could have lots of different models in slightly different models, different decision trees, but able to work on the same data and giving you independent predictions on the same data point and taking majority voting. This is very tempting. However, the problem is, how would you apply this idea when in fact you realize that, once you are given a training data set, you in fact build a single decision tree. All these algorithms that we've discussed over several videos on how to build the decision trees, they are deterministic. So for a single training data set, you will have a single decision tree. And this whole idea here depends on the ability of having a number of different binary classifiers. Even though they are weak, they should be different. They should give you different opinions, and then you would take the majority voting, and that would solve really the problem. So for us, this is the problem that we need to solve, and the solution has been known for a long time. The solution is called bootstrapping, and that is that you would generate multiple samples of your training data. In other words, if I am to use, again, the statistical terminology, this would be random sampling with replacement. So what this means is that you are indeed given a single training data set, but what you are going to do is you are going to build the first decision tree on just a subset of the training dataset, and that subset is going to be chosen randomly out of your training dataset. And you build your decision tree. This is done with replacement, so those data points you selected to train the first decision tree, they are put back into your data set, and then you start building the second decision tree on a different random sampling of your training data set. Because the points that were participating in the first tree were put back, there is a chance they will be selected again, but there is also a good chance that other data points are being selected. So this is the idea of bootstrapping or random sampling with replacement. So you are going to generate a decision tree for each such variant, or for each such sample, if you wish, of the training data set. And then you are going to do, an aggregate. So you have a number of decision trees, and when you have to give a prediction for a data point, you are going to give the prediction as being the average of the outputs of all the models that you have built. So this is, as simple as that. There isn't much more to say. There is something that I want to say in terms of how do you measure the errors of such models. And there is something subtle in here, because you optimize, as always, you optimize on the training data points, and when it comes to measuring errors and, comparing the performance of different trees, you don't want to measure the error on data points that contributed to optimizing that model. So in other words, you would like to measure whatever error function you have, you would like to measure it on data points that did not participate in optimizing that decision tree. So this idea, again, is known for a long time. This is called out-of-bag error, or you can write it down as OOB, out-of-bag error. And the point here is that for each data point in a training data set, you only take the predictions of the models that didn't see that data point during training. And so that's going to give you a sort of robust measure of error, because they were really not seen by that model. The model was not optimized on them. And one advantage of this is that you don't need any more cross-validation. The idea of cross-validation was exactly this, that you build on some parts of your data and you validate on some other parts, and you do this a number of times. This one, with bootstrapping and aggregation and out-of-bag error, replaces very clearly the need for cross-validation. And so this all together, the idea of bootstrapping and aggregate in one compressed and combined word, is called bagging. This comes from putting together bootstrap and aggregating, and this concept and this term was proposed in a paper in 1996. So this works very well in terms of the performance of your models, kind of just following up with calculations of this type. It's going to, even though your decision trees, each one of them is relatively weak, when you build enough of them and you take them together, they will improve the performance. There are several weaknesses, and one is, and this is going to be the case for all the ensemble models that we are discussing, this is going to be a systematic weakness. Your model is going to be less interpretable because the overall model is larger. In terms of giving decision paths and decision rules for a data point, that's going to be made up now by decision paths in several, possibly many decision trees. The other weakness that in fact we can do something about is that, if in your data set you have some features that are highly correlated to the target, even though in bootstrapping you don't take the entire training data set, you just take a subset of the sample, those samples always come with these features that are highly correlated potentially with the target. So that means that when you build your decision tree, the splits you are choosing are going to be always on these features that have a high correlation to the target. So in other words, even though you were hoping for decision trees that are different, just this idea that you have highly correlated features with the target is going to show you that in fact the decision trees you build are going to be quite similar to each other. So that's a fundamental problem in this bagging approach, and that's something that is being solved in the random forest. So when you go from bagging to random forest, you really address exactly this problem. So you have just one additional key idea, and you would say, what if in each bootstrapping tree, in each tree that I'm building, I'm going to consider just a subset of the features. So I don't take all the features, but just a subset of them, and you select them randomly from your training dataset. So the way, put together, the way this would go for random forest would be like this. You're going to build a number of decision trees, and for each decision tree, you're going to generate, first of all, multiple samples, subsets of your training data set. In other words, not all data points are selected for each tree, but just a subset of them chosen randomly. And this is going to be a sampling with replacement. You put them back, they have a chance to contribute also to other trees. For each training subset, you select a random subset of features. And then you are going to generate a decision tree for each such training subset. So fewer data points, fewer features than in a full data set. And you do that a number of times, however many decision trees you choose to build for your random forest. And then the output of the prediction of the random forest is going to be an aggregation of the outputs of the decision trees contributing to that forest. And the result is good. This is going to give you more variation between the trees, because you take different features for each tree. They will see different features during the training. Also, they will see different data points. So because of that, you are going to reduce even further the variance. And this is something that was proposed in a paper in 2001. And I have this, plot that I want to show in here. You remember when we discussed about decision trees and decision boundaries, we discussed about this idea that they are splitting the data space into boxes. They always, each decision they make can be translated into a split in the data space with a vertical line or a horizontal line if I am to talk in 2 dimensions, with a hyperplane aligned with the axis if I am to talk in general for higher number of features. Now with random forest, the situation is different, because having more decision trees, even if each one of them is a combination of such piecewise linear constant functions, when you put them together, you get in fact this sort of smoother decision boundary. And the more decision trees you get, the more smooth this decision boundary is going to get. So in this particular example, this is a data set called half moons. You have one half moon here. This is one class, this is the other class, and this would be impossible really to classify with just a single decision trees. But as you can see, the decision boundary is quite successful with random forest. There is another idea that I want to discuss now. Another type of ensemble model based on decision trees, and that is extremely randomized trees. And the way, the key concept for such models is really the same as in random forest. You are still going to do a bootstrap sample of the training data, and you are still going to do a random subsample of the features, so exactly like in the random forests. But there is an additional key idea. And that is, if you think about the way you are building decision trees, instead of finding the best split on those features, and remember, this was a greedy approach, this was local optimum, so instead of doing that, which comes from the decision trees and really is taken to random forest, what you are going to do in this case, you are going to say, let me just try one random split. I don't care about the optimum split. I'm going to do just one random split on each one of these M features, and I'm going to select the best among them. So in other words, rather than going with this greedy approach, you are taking more of a random walk in terms of how to build an optimal tree. And this is a method that's popular, and it's actually implemented and available in popular libraries. For example, in sklearn it is available under the name extra trees. Another possibility for ensemble models, based on decision trees, is the idea of boosting. And I want to spend some time on discussing this idea of boosting and gradient boosting of decision trees. The key concept in boosted trees is quite different than that in random forest. So this time you are going to start with a decision tree, and then you do your best of building it with whatever pruning and whatever constraints you want to put on that. And then what you are going to say will be, let me look at the sort of errors or the loss that this decision tree makes. And I'm going to try to build a second tree that's focused exactly on this loss. It's going to really focus on this loss and will attempt to improve the first decision tree by considering as targets these loss these loss values. And once you build this second tree, the prediction of the model that you are building at the moment is going to be the sum of the predictions of the first and of the second tree. This new model, again, is going to have some error. Again, there will be some loss. And then you say, okay, let me boost it even further. I'm going to build a third tree, and that's going to focus on the loss of the previous model, which is the sum of the previous two. And so you continue boosting this until the collective sequence of models gets closer and closer to the values that you are trying to predict. So I want to write down some of these things on the slide and give you somewhat more precise definitions. And I'm going to consider the case of a regressor simply because it's more intuitive in terms of thinking about losses and cumulative losses and so on. But the idea is exactly the same for a classifier as well. So again, I'm going to just write down this that we have a data set consisting of points xt, yt. We have this many data points, and the labels are real numbers. And you are going to train, like I said, one decision tree to start with, and this first decision tree, so you are going to denote its predictions in terms of a function f1. And so the prediction of this tree, prediction on data point xt, is going to be simply f1 of xt. And so the training error, or residual if you want to call it, is going to be just the difference between the real value and the prediction. And then you follow up and you say, what, I'm going to have a second tree, and that second tree is going to focus exactly on these residuals. So the second tree is going to be trained on this data set. It's going to be points xt, but as a value they will get exactly the residuals. So what's left after the first model made its predictions. And I'm going to denote the predictions. So prediction of this tree, I'm going to denote it as function h2, and the overall predictions, so overall predictions of these combined models that I'm building is going to be, I will denote this by f2, and that's going to be exactly what I had from the previous model, plus the prediction of this second tree. And the training error of my combined model so far, so training error, or again residual, that's going to be again the difference between the label and the prediction we have at this point. And this continues, if you build the mth tree, then you are going to get the residuals of the m minus first tree, and so on. So the full formulation of this idea of gradient boosting is going to be simply that you are going to build a number of trees, and when it comes to the mth tree, the prediction overall, so of all the trees from the first one to the mth one, is going to be dependent on the prediction of the previous tree plus this performance of the last tree you have trained on the residuals of the previous one, so this hm of xt. And I'm also writing it here because, I mean, you want to sort of dampen down the effect of these residuals. You want to encourage the model to converge. So typically this is multiplied here with some factor. So this theta is the learning factor. I want to end with one slide with a timeline over various forms of gradient boosting. The first time this was introduced was around the year 2000, and this was exactly the concept that I had on the previous slide of boosting your first decision tree with a number of additional trees, focusing each time on the residuals left from the previous ones in the sequence. And this was very quickly adopted in the sklearn library, so that made it quite popular and widely used in practice. If there is a weakness about this implementation is that it's single-threaded, meaning that it tends to be quite slow in practice. And addressing that, a number of years later, XGBoost was proposed. The implementation in terms of programming language and other tricks is there, and this was and is much faster. It's also much more able to deal with missing values, whereas this one you have to do data imputation before you apply it. And then the latest additions to gradient boosting are LightGBM and CatBoost, each one of them with different advantages. For example, CatBoost was really introduced with the idea of focusing on support for categorical features, and it does very well on mixed data, numerical and categorical features. This LightGBM was introduced with the idea of being very fast, and indeed it is. It's also using quite low memory, and so this tends to be quite good for large numerical data sets.